Well, thank you very much. I particularly want to thank NER for inviting me to this symposium and for releasing me from Ann Arbor, where the temperature is right now minus 20 degrees centigrade. So I've left my students behind. I hope I still have them when I get back. Today, actually, NER challenged me to talk about two things, not just one, but they're very related. And it's thin, excuse me, thin film solar cells on plastic. I have a split personality. I work in both 3.5 semiconductors and organics, and there actually happens to be a commonality. So today I'm going to take you through both of those technologies and show how they converge and where they actually might make a big difference in how we generate energy. So initially I'm just going to talk about a comparison of organic and inorganic materials. Then I'm going to talk about some unusual ways to make actually low-cost gallium arsenide-based solar cells, and that's a hard thing to say because the wafer cost for gallium arsenide is about $20,000 per square meter. So how do we get to $1 per watt or less? Then I'll go to perhaps the more obvious material system for this, and that's organics, and then we'll combine the two. Is there room for innovation there? So let me just do a couple comparisons between organics and inorganics. I've just put them up here. A minus means bad, a plus means good, and a zero means I don't really know. The cost, obviously, of inorganics is very high. Inorganics are dye stuffs that we use in everyday processes like clothing and so on. It's low temperature, so it can be green processing, which means low cost again. Inorganics are much more robust to chemical attack, so they're much easier to pattern ultimately. And you can go down through this list one at a time. I think one of the things that we need to talk about during this talk is reliability of organics and efficiency. And so we'll talk about both of those things. And you can see those are where inorganics really win, and organics are very questionable. So if we just look at the electronic properties of these types of semiconductors, there are very fundamental differences, and they make them very exciting. And actually, I'm getting more and more into looking into hybrids between organics and inorganics, because you can actually combine these materials in heterojunctions to take advantage of the good properties of both and hopefully leave some of the bad properties of each behind. Primarily, organic materials are known as excitonic materials. All of their optical properties really come from the fact that you create a molecular excited state, whereas and it's very tightly bound because of the low dielectric constant. The low dielectric constant, of course, also results in a small exciton radius and a very large binding energy. In inorganic semiconductors, unless you make an engineered structure, excitons don't play a particularly significant role. It's mostly band-to-band excitations, but if you do happen to create an exciton just below the band gap, it's going to be a 1A Mott type of species. It's going to be quite large, extending over many lattice constants with a very low binding energy, typically unstable at room temperature. One of the reasons we like organics so much for optical devices is they have extremely high absorption coefficients, which is characteristic of most two-level systems. But then you're saddled by a low mobility. So you can see that there's sort of a yin and a yang here, that there's things that you can, if you could only harvest the good properties of each, you'd have the ideal semiconductor. Unfortunately, I don't think nature arranged it that way for us. Just to bring everybody up to speed, organics are a big industry today. It's approximately $8 billion this year, last year, 2013. Probably this year it'll be about $12 billion, maybe more. Where if you have a Galaxy phone, you're using OLEDs, phosphorescent OLEDs, and Samsung alone has produced 40 million OLED displays. You can now buy in the United States an LG 55-inch TV and it is absolutely gorgeous, and it has a price to match. You can see the price is absolutely plummeting. Went from $9,000 for a 55-inch display to $8,800 after it was on the market for about 7 months. But I would encourage you to wait a bit. And this is the Samsung display, the 55-inch, and it's curved, and they're really nifty. And you can buy flexible phones now and things like that. So this is a big industry, and I'll probably end up making a few predictions during my talk. One of my predictions is that OLEDs will become the dominant display technology in between 5 and 10 years. So if you're working on LCDs, hopefully you'll retire soon. Okay. So now let's go back to photovoltaics. And this is where we started to get really involved with gallium arsenide. Again, my lab and my life has been split since almost the beginning when I was at Bell Labs between interest in organics and inorganic semiconductors. And if you look where inorganics really win, particularly gallium arsenide, is in what's called the specific power generation efficiency. And you can get 6 watts per gram of this stuff. It's extraordinary. So if you want to launch it into space, which NASA always likes to do, or make mini robots, which the Army does, and we have a program with the Army, these little things that fly into rooms, take pictures all around and then fly out. Putting them on wings and things like that is really a good value. And also for soldiers on the move and so on to have portable panels. Organics, interestingly enough, don't stack up so good because their watts per meter squared is lower. But these are very, very lightweight. They take very little material. So that's where we got interested in them. Unfortunately, they're hugely expensive, which is why only NASA and the Army really care about it. So let me just levelize everybody's expectations. This is where the world of solar cells exists today. The theoretical limit for a single junction cell is 31%. The highest efficiency that I'm aware of for multi-junction solar cells under concentrated sunlight is 46%, but that's a multi-junction cell, so it can break the limit there. The record single junction solar cell is 28.6%. That was announced by Alta Devices not long ago. Silicon solar cells are in the laboratory about 24%, but when you put them out in the field, they're somewhere between 16 and 18% for good silicon solar cells. I'll talk about organic solar cell today, and that's a number that's coming out of our lab, but we don't look at that as an endpoint. So where is the endpoint? My student some time ago looked at the basic processes of charge generation, photogeneration in exotonic materials, and he was able to calculate, among many other things, the thermodynamic limit of efficiency for organic cells. This is the Shockley-Queisser limit of about 31%. It depends a little bit on some of the assumptions you use, but 31% is a pretty good number. And you can see that the optimum band gap, interestingly, is right about where gallium arsenide is. Perfect. And the best anybody's ever gotten, as I mentioned, is 28.6%, I believe. And that's because you make certain assumptions, like the sun is a black body source at 5770K, and the absorption coefficient is well, basically, you get 100% internal quantum efficiency from the band edge up, and so you can't really get to that limit. If you look at organics, because there's I'll talk about the relaxation that occurs in the exotonic state on absorption, you get sort of a range of efficiencies here, which depends on really the dielectric properties of the organic, and I think it's safe to say that we live somewhere in there, which is again at about 1.4 EV, and it comes out to 25%. So we have a target that's actually pretty worth pursuing. It's not quite the 31%, but then again, we can go to multi-junction cells, and I'll spend a fair amount of time talking about that. So now let me talk about inorganics and see if I can convince you that even at $20,000 per square meter, this stuff can really be cheap. That's a tough one. I'm not even sure I believe it. No, I really do. This is the way we look at solar cells today. This is silicon. It's out there. It's running today at about 85 cents per watt. Really the problem is that these modules are very heavy. So it takes a lot of support structure and a lot of infrastructure to turn solar energy into real energy. And one of the things I like to remind people is if you gave the module away for free, it would still cost more than fossil fuel solar would, because you have all this other stuff you have to make around it. And fossil fuel today is extremely inexpensive, which is another problem. Now, gallium arsenide, you can see this is the cells in our laboratory. It's on plastic, very thin, very bendable, very lightweight, so you don't need all this support stuff. You can still need inverters and all the other stuff to turn DC into AC, but all electricity has to be conditioned no matter where it comes from. So now I'm going to talk about how to get the cost down. Way back in the day, in 1987, Jablonowicz demonstrated solar cells by a process called epitaxial liftoff, where basically you grow your epitaxy on top of your wafer. You have some sacrificial layer. I'll show you this in a little bit more detail coming up. You etch out the sacrificial layer that peels off your epi. You glue it to a handle, then you transfer it to another substrate. That looked like it was really going to go far. The problem is that when you etch away that sacrificial layer, you leave damage on the substrate. And so you have to polish the substrate. Once you have to polish the substrate, you can use the substrate maybe 3 or 4 times and you're done, if you can do it that many times. I think the limit of that process has been about 5 with polishing. $20,000 per square meter, you're not, all right, so now you're down at what, $4,000 per square meter. It's not a big jump. We came up with, or my students came up with not long ago, this concept of epitaxial protection layers that allowed the wafer to remain in its pristine state after you peeled off the material. Further, we never use any glues. We just cold weld, and I'll talk about that, the epi to a plastic substrate without any adhesive. So it's extremely flexible and very cheap and extremely lightweight. Adhesives tend to crack and be bulky and heavy. And so that leads us to multiple growths, basically an indefinite number of growths on a single wafer. So now you've turned your very expensive wafer into capital equipment. It's just part of the equipment. And you just keep doing it over and over and over again. So this is the life cycle of what we do. We grow our layers. We cold weld bond the epi with the wafer to a plastic substrate that is coated with gold, very much like your sandwich bags or whatever, potato chip bags. We then peel off non-destructively the epi, leaving it on the plastic substrate. We process our cells. We take that wafer, we clean it without polishing, and put it back in the system, and do that round and round and round. This is the structure. It looks pretty complicated, but it isn't, because this from here up is just how you make a solar cell today, a gallium arsenide solar cell. And then this is our world of protection layers. We start with the aluminum arsenide, which is our sacrificial layer, and you'll notice we've got gallium arsenide, indium gallium phosphide, gallium arsenide, indium gallium phosphide down in the substrate. And there's the bonding process again. Now the cold weld process that's shown here, basically take 2 clean metal surfaces and you press them together. This was something that I learned how to do in Bell Labs when we were putting LEDs on headers. But we simplified it greatly. We then moved that process to making OLEDs by putting down the contact here. Basically, when you take a noble metal and you press it together and you shrink that distance d, there's basically a bonding energy, but there's some surface contamination. You have to press through it. It takes a little bit of pressure. If it's clean, it doesn't take a lot. And then there's this what's so-called avalanche, and that avalanche means that the electron system all of a sudden gets shared between the two surfaces, and it forgets there was ever a difference. And so this is much stronger than any adhesive you can ever put on. As a matter of fact, it just looks like a thicker layer of gold, which is ideal for flexibility and for durability. Well, we thought we were pretty smart, but then we learned that we were beat. This is really getting scooped. This is being scooped by 4,000 years. And this is a bronze dagger. And they've done something really nice because they've got both gold and silver plated on that dagger blade. And it's just done by cold welding. So if you think you really have invented something new, forget about it. So this is just some of the things that we've done. We've made an imaging array of organic devices by cold welding. Basically, we cold weld an array of lines. In one direction, we deposit the organic, and we then turn the substrate over and do it. This was to make an artificial eye type of arrangement, where we just have a single lens. And basically, what we're doing is we put the gold on an elastomer, we suck it into a vacuum, and we put a little gold on top of the substrate, and we then lift off these lines. We clean up the area between the lines, and we can make these arrays. And we did that some time ago. This is another thing we did, which was these electrically small antennas, and you can see the patterns that are just, you don't have to write them or anything like that. You just put them on these elastomeric things, and you suck them into a vacuum mold, and we're making these for the aerospace industry. So you can do this and use it for a lot of processes. We basically make a whole bunches of different devices using this printing process, which I'll get back to later on. Okay, so let me go back to this non-destructive process. This is the generic wafer. You can see there's a gold bond to the kapton that we use for the plastic substrate. This red line is the sacrificial layer. We just basically use HF to etch that out, and then we have these protection layers. Now, as I mentioned, when you do that, you're left with a surface that's loaded with these little stones. This is the wafer surface after you do the epitaxial liftoff, and this is what people have been dealing with for decades. And these little stones are arsenic oxide particles, and those particles are very inert. There's very little that takes them off. So the first thing we do, which kind of preps the surface, so this is the gallium arsenide wafer substrate. The epi is gone. It's sitting on some plastic somewhere else. We use a little plasma to, this is a remote coupled plasma of sulfur hexafluoride, just to clean it up. This is still not good enough. You can see it really loses the roughness, and we get back to smooth plates. But now we're on indium gallium phosphide. So we have the indium gallium phosphide. Let's see. We've taken off the arsenic, aluminum arsenide. That's the sacrificial layer. And we're left with this. Now it's fairly clean. And now we use a selective etch that, although this is maybe still slightly rough, but it doesn't have the arsenic oxide on it anymore, we can then etch this with a selective etchant and remove it right down to the gallium arsenide. And then we can use now another selective etchant to move it down to there. Actually, we've gotten rid of the last indium gallium arsenide phosphide layer. And you can see that this is a fresh wafer from the vendor, and this is the protected wafer. It's absolutely pristine. This is the detail. I don't want to get into it, but you can use a little bit of the strain of the substrate to really make the epitaxial liftoff fast. We put a little iridium on it, and it curls the plastic before we put on the gold, and it creates a cavity there to speed things up. And the next couple of view graphs just show what's going on. This is one of those arsenic oxide little guys here. This is XPS data, and you can see it. And then after it's been processed, that peak is way down. This shows the original wafer. You just have to always get back to the original. So just some more stuff to show that the read pattern of the original and the read pattern of the processed wafer is identical. But when you go through this center point where you have to, if you didn't do it our way, you'd have to polish it, and that polish takes off 10 microns, you really don't have many cycles left for you. And you can keep doing it. This just shows the interfaces, the regrowth interfaces, second regrowth, first regrowth, and so on. I'm just trying to show you that we really do return back to the original wafer. And then you have a device, and this is the basic structure. This shows kind of what happens after 3 of these processes. I have a student, so we can't do it 50 times without him quitting on the 3rd, 4th time. So we did it 3 times, and you can see everything we measure is quite comprehensive. There's nothing systematic going on. We have very nice IV characteristics, and you can see the types of efficiencies we're getting routinely. These are not really super duper wafers. They're just good enough. You know, like I said, the best is 28.6. I think before that, the best was somewhere around 26% or something like that. But most people make 24% gallium arsenide wafers, which isn't bad. And you can see the quantum efficiency is 95% over an awful lot of the spectrum. One kind of cool thing, which is, to me, it's all about form factor and expense. You first of all got to get rid of the wafer expense, but you also got to get rid of the, you have to make it very lightweight. And this is where we're curling these wafers over, or these, we got the plastic, we have the epi on top of it. And surprisingly, we can get these right down to about a centimeter radius of curvature without damage to the wafer. At some point, you start to get dislocations forming like crazy. So this is very lightweight. You can deploy it in rolls, and you get 24% out of it. It's not too bad. So this is the economics. This is not careful or comprehensive modeling of the economics, but here we started out, we tried to be really aggressive on the cost that we're going to order barrels of gallium arsenide wafers, so we said it's only $17,000 per meter squared, and that's 56 6-inch wafers. You have to square them up because you don't want to waste any material, and that comes to $340 per square meter if you can reuse it 50 times. If you have absolutely no damage, you should be able to do that. And I'm not going to talk about handling, you know, dropping or anything like that. You have to come up with mechanisms to really watch your wafers because you really want them to be part of the capital equipment. The source material is this, electricity, about 120 kilowatt hours to grow this stuff. Wafer processing, the total is $430 per square meter. If we have a 30% power conversion efficiency, if we make a multiple junction cell, let's say, but no concentration, we're about $1.40 per watt, which is still nearly double silicon. But now we can do one thing, which I'll show you next, very briefly, is we can put mini concentrators on these things without optical, without beam steering of the solar cells, and that just drops right to the bottom line. If you get a 4x concentration, that just divides that by 4. If it's 10x, it's 14 cents per watt. So how would you do that? We just have a very small demonstration here where we're gearing up to do it much differently and much more practically. But basically, we've made these in plastic, which we coated with I believe this is aluminum. It might be silver. We take it, instead of a full wafer, we just take a strip of this gallium arsenide and we put it down at the bottom of this compound concentrator. And if you tilt it toward the declination of the sun does this. And I could show this in winter and summer without changing that angle. But this is what happens to a flat cell. That's during the day. That's what the solar energy is doing, or the power generation. This is tracking a flat cell, and this is with these mini concentrators. And this just shows the thing working for us here. So without even steering this thing, without adjusting for the sun's position, because these are cylindrical, you can get quite a bit more area under there. So that's one type of cell. Now I'm going to quickly go to the second cell, and I have to be very quick. But organics provide us with a significant challenge in that we don't generate free charge by the absorption of a photon. What we do is we come in with a photon and we create a molecular excited state called an exciton that has to drift toward a junction, and that electron then sees the conduction level of what's called the acceptor molecule. So there's a junction between a donor layer and an acceptor layer, and it sees that its energy is more favorable on this side, and it creates what's called a polar unpaired charge transfer state, where the electron and hole are bound across that interface, but eventually they work themselves loose and you get charge out. And this is a pretty complicated process. There are 4 different steps to it, and the efficiency is the product of all those steps. So if any step is less than 1, it's going to hurt you. And people have been working a long time on maximizing this, these efficiencies. The biggest problem is that although these are highly absorptive materials, it takes a long distance on the order of 1,000 angstroms for a photon to be absorbed. But it only is about, the excited state can only drift about 100 angstroms before it can, before it basically non-radiative recombines and you lose your energy. So there's been a lot of solutions to this. Now in the polymer world, people have, it was really Alan Heeger who demonstrated the first bulk heterojunction device, where he took 2 polymers which were partially miscible, and they separate the donor and acceptor, and they form this kind of entangled thing here, so that in a sense it divides it separates the dimensionality of the problem into two dimensions. The photon can be absorbed along the fingers, but the exciton only has to drift sideways. These are small molecule solutions to this that we have been working on over the years. They're not exactly the same thing as a bulk heterojunction cell, we call them nanocrystalline cells. But these things have really been, whatever you call them, have been quite successful in increasing the efficiency. So these are the solar cell challenges. We need high efficiency, I think greater than 15% to be really commercially interesting. We need large modules. This was the largest module ever made in my lab in about 2004 or 2005. We never tried it again since. These are centimeter squares, and I think there's 24 of them. 16 of them work. So we had it was about a 10-volt cell. It wasn't very efficient, but it was kind of interesting to build. High reliability, which I'll talk about, and of course, low production cost. So I'm going to show you one single junction cell. These are all small molecule, and just to give you a sense of how we make them, we have been focusing on what we call the planar mixed nanocrystalline heterojunction cell, where we take the donor and acceptor and we mix them, we blend them, very much like the bulk heterojunction. And so we have a donor and acceptor layer here, and we put on top of it, this is the planar part of it, we put another acceptor over here. So we're using C70, which is broadly absorbing across the visible, as the acceptor. And you can see its energy levels extend across because we also have a blocking layer. And the blocking layer is very important because if an exciton is generated here, it can easily drift over to the silver and quench. And also you want the optical field to be maximum in this active region. And of course, we know that the optical field has a node at the silver contact. So therefore, the maximum has to be placed somewhere in here. So this has to be a transparent, wide energy gap region. And our best solution to this was to mix the fullerene C60 into a very wide band gap transparent material. And the C60 forms these little wires. And we call this an exciton filter, or an electron filter, because you have a small drift field across this thing. It's the built-in voltage. And electrons can find their way onto these wires, and because of the symmetry of C60, they form these chains, and it's quite conducting. But excitons are a little bit bigger, and they don't quite know what to do. They really can't transfer energy very effectively to the C60, and so they bounce off. And so this is a highly transparent, very highly conductive buffer. And this is, by the way, just the structure of the donor and the acceptor. You can see C60 looks like a underinflated soccer ball. And this turns out to be a really terrific way to build solar cells with these buffers. And you can see it here. This is a single junction cell. This is 8.1% power conversion efficiency cell. And these are just different buffers. This was the first buffer we ever tried back in the year 2001 or something like that. Back then we were making 1% and 2% cells, but if we use that buffer with these really good materials, we get to 7.1%, and here we get to 8.1% with this better buffer. So the buffer is really crucial. And you can see that the the quantum efficiency of these things, this is the internal quantum efficiency on this side, and this is the absorption percent on this side. And you can see that it's sitting up there in the 90% range. So this is looking pretty good. It falls off, unfortunately, at too early a stage. So now let's put them in a stack device and see what we can get with that. So here we're using some materials that were supplied to me by Mark Thompson at the University of Southern California, my long-term collaborator. We put down a solution process blended squarane, which is a bit different than that other donor. C70 here. We need to have a charge recombination layer down here, and for this we use about 1 angstrom of silver. It makes little nanodots or nanoparticles, so that when a hole, let's say it's going to be an electron that drifts up from this side, when it sees the sphere, it sees its image, and it gets attracted to that image. And so now you have a negatively charged silver particle. A hole from this side comes in, and it sees the negatively charged nanoparticle, and it then recombines there. So you got to get rid of those internal charges. And the silver, just a whiff of it, gives you an extraordinary efficiency for doing that. The nice thing about this is it has 2 cells, and they're in series, so you get twice the voltage. And everybody knows that you need more voltage than current if you want to have high efficiency. So these give you high voltage, good current, and they're pretty simple to make. And with this one, now I just showed you an 8.1% single junction cell. This was done a little bit before that, so it's not fair, but we only got to 8.3% at the time. We thought we were really doing quite well. And you can see this thing has a 60% efficiency across the board. More recently, we've taken donors which absorb as far out in the IR as we can get them, and now we've got a cell, one of the subcells is absorbing out here, and the other subcell is absorbing here, so they're not overlapping, they're spectrally complementary. And with this particular device, you can see the voltage. This is the 4th quadrant IV characteristics. The voltage is quite high, and we get to 10%. What did I just do? Oh, well. I'm not showing you the really nifty cell, which is 11.1%, but I guess I forgot it. Oh well, it's just a number. Next week it'll be higher. That's the thing that's happening, actually. It's true. You know, people are understanding so much about the technology today that the progress has been extremely rapid. I am absolutely certain with our own solutions we'll be at close to 15%. You know, in a year or so. But this is something we have to be aware of, is organics are not as long-lived as inorganic materials. We've really made a study of this for OLEDs, because there's a big problem in OLEDs. The blues are much shorter lived than the greens and reds, and that's been a problem for the display and lighting industries. And we started to look at the very fundamental processes of why OLEDs decay, and they're pretty similar to this, but now we've applied it to solar cells. And this just shows a mixed subphthalocyanine C60 cell. But basically what's happening, and you can fit the curves, et cetera, using basic rate equations. You have an energetic exciton that sits up in this excited state, and when it non-radiatively falls back to the ground state, it can dump all of its energy into a bond. And that bond can then dissociate. So the molecule actually goes into a dissociative state. And that's one of the primary mechanisms for these things to die. Now, contrary to OLEDs, with OLEDs, the higher efficiency, the longer the lifetime, because that means to get a certain brightness, you don't have to drive them very hard. But with the PV cell, the higher the efficiency, the shorter the lifetime, because the current is higher. So it goes exactly in the wrong direction. This just shows one of our cells, and you can see this is the power conversion efficiency over a period of 70 days of continuous illumination. Oh, this is, I'm sorry, this is at 40 centigrade on up to 90 centigrade, and you can see that it's certainly thermally activated. With that thermal activation, for this particular system, we get 450 millielectron volts. For this particular system, to get to 80% of the initial time, which is somewhere out here, it's our best devices are at 1,500 days, which is what, 3 years. But that's for a mixed junction. And the reason a mixed junction works so much better than a planar junction is because the exciton immediately dissociates. Every time an exciton is formed on a molecule, it's a donor molecule, but it's all mixed up with the acceptor molecule, so it immediately splits, has a very short lifetime, and can't undergo this dissociation. So this sort of summarizes where organic solar cells sit today. These maize and blue circles are some of ours. Those are the colors of the University of Michigan. The solid circles are polymers, and the open circles are small molecules. All of ours are small molecule. And this is the thermodynamic limit. So you look at that and you say, oh my goodness, we're almost there. But this is log scale, so we have a ways to go. And this is amorphous silicon. It's sort of a cautionary tale. Amorphous silicon is a dead technology. 5 years ago, it was thought to be the thing that was going to take over the world, but then the cost of crystalline silicon went so far down, and polycrystalline really collapsed, that amorphous silicon just vanished from the face of the earth. And they got up to about 12%, which is about where we are today. But we see that we're going to be getting up much higher than that. Some economics again, just to round it out. 20 cents is, I think, very doable. That's kind of with the efficiencies that are in the ballpark of where we are today. If we get up to 20% in a tandem cell, you know, we're talking 10, 15 cents per watt. But it's got that low form factor. It is rollable. It is all the things you need to lightweight, to make bring down the levelized cost of electricity, all the other stuff that goes around it. And this is the idea. I think it brings us home to this conference, which is the promise of organic electronics. I love organic electronics because there's so much good physics and engineering to do with it. But you know, frankly, the world's interested in it because it's cheap and there's money in it. And this is where the world thinks this is going. And that's why, of course, they're investing in our research. But it's to turn out organic electronics, in this case solar cells, by the mile, the same way you print newspapers. The older people in this room probably know what a newspaper is. The rest of you just read it on the web. But you know, you print out miles of paper and don't think about it. But those dyes are very similar to the dyes that are semiconductors used in these materials. So there's no reason we really can't get to this vision. My last view graph before the summary is just to show that if you put a little bit of organic, a very thin, just a couple of nanometers, onto the surface of an inorganic semiconductor, we call this a window layer, it increases. This is a Schottky barrier device. This has an ITO contact on it. We put this very thin PT-CdA layer on top of it, and it increases the barrier height. And that increase in the barrier height increases the open circuit voltage. And we go from, we get about 2% more power conversion efficiency out of this indium phosphide cell, which is about 15%, just by putting on this very thin, basically free and quite environmentally robust PTCDA layer underneath the contact. So this is one way we can use organics. The other thing is you can actually harvest sunlight with those things too and drive those excitons to this interface, and we have recently managed to do that as well. So it's kind of a fast excursion through two technologies, but in our mind they're serving the same purpose, which is to deliver high efficiency and lightweight and and deployability for power generation. The gallium arsenide thin film solar cells can be affordable. We absolutely are confident that that's true, but we need to use this non-destructive epitaxial liftoff. Organic solar cells are very low cost, low energy to manufacture. Efficiencies are zooming up. And possibilities to combine the best of both worlds may be very speculative in that one, in organic, inorganic cells. All of these technologies can be lightweight and flexible, which is definitely a different way to be looking at solar cells today. These are the people who contributed to this. I'm really doing a disservice to my group because this is a lot of work over many years. These are just the most recent people who've contributed to a lot of the stuff that you've seen. Q-Song Lee is the gallium arsenide guy. All the rest are ganged up against them. Those are the organic people. We've had a lot of collaborations, particularly Mark Thompson's group at USC has been my long-term collaborator, actually now for 20 years. If you ever want to see a materials genius, that's the guy. And then we get a lot of money from particularly the Department of Energy and some of our commercial friends. So thank you very much.